So at this point in Chapter 3, we've gone over Introduction to Vectors and Vector Operations. We've covered projectile motion. Now we're on to the final topic, relative motion. So relative motion is going to come back to a concept we discussed in Chapter 2, frames of reference. This is your perspective, or how you're viewing the objects in the situation as you solve the problem. So for example, maybe you're riding your unicycle at 25 miles per hour, as you can see here, and a car passes you traveling at 35 miles per hour. Because you're not standing still on the road, you're moving, you have a moving frame of reference. This means that rather than viewing the car's speed as a full 35 miles per hour, you're only going to view it as 10 miles per hour as you move along next to the car. Let me explain that a little bit more. Calculating relative velocity. So here we have two cars. The first car is traveling at 20 meters per second, while the second car is traveling at 13 meters per second. Your goal is going to be to find the relative velocity of car 1 relative to car 2. So let's start by using some notation here. I'm going to teach you a way to write relative velocity. We're going to call the relative velocity of car 1 relative to car 2 v1 over 2. This means the velocity of car 1 relative to car 2. To find this, we're going to bring in the velocity of the two cars relative to the Earth. So velocity of car 1 relative to the Earth plus velocity of the Earth relative to car 2. You can think of this addition problem as canceling out the Earth to leave you with velocity of 1 relative to 2. So we're trying to solve for v of 1 relative to 2. So v1 relative to the Earth, that's easy. We know that the car is traveling at 20 meters per second. That's its velocity relative to the ground on which it's driving. Now for the slightly trickier part, the velocity of the Earth relative to car 2. If car 2 is traveling this way at 13 meters per second, the Earth, compared to a car 2, is traveling in the opposite direction at 13 meters per second. This means we're going to switch the sign to make it negative 13 meters per second. So we'll call that 20 plus negative 13. We get a final answer. The velocity of car 1 relative to car 2 is 7 meters per second. Let's do some practice with relative motion. A woman rides her bike at 9 meters per second relative to the ground. So let's see, we'll call this v bike relative to ground equals 9. And passes a boy on a tricycle who's traveling 1 meters per second in the other direction. So the velocity of the tricycle relative to the ground is negative 1. Now we're solving for the velocity of the tricycle relative to the bike. Okay, so vt relative to b. We're solving for that. So let's set up the addition problem once again. The velocity of the tricycle relative to the bike will be equal to the velocity of the tricycle relative to the ground plus the velocity of the ground relative to the bicycle. So velocity of tricycle relative to the ground. We already have that. That's going to be negative 1. Now we need the velocity of the ground relative to the bike. If the bike is moving in this direction at 9 meters per second, the ground will seem to be moving the other direction, negative 9. So we'll call this negative 9 meters per second. Negative 1 minus negative 9 is the final answer of negative 10 meters per second. That's how fast the tricycle appears to be moving relative to the woman on the bike. On to another relative motion problem. Number 2. A passenger in a train moving at 15 meters per second throws a ball at 15 meters per second from the back window. How fast is the ball moving relative to the ground upon release? So you already might have a guess as to the answer of this problem, but let's work it out the way we've learned before. We're looking for the velocity of the ball relative to the ground. We'll see that that's equal to the velocity of the ball relative to the train plus the velocity of the train relative to the ground. So v over g. So the velocity of the ball relative to the train. If we're throwing it out at 15 meters per second, we'll call it negative 15 because it's going out the back in the opposite direction. Plus velocity of train relative to the ground, well, the train is moving forward at 15 meters per second. We'll call that positive 15. we get that the velocity of the ball relative to the ground is 0 meters per second. So to an onlooker by the side of the tracks, upon release, the ball would be moving at 0 meters per second.